Welcome everyone to the second week of the exciting topic of stream ciphers. What the 90 minutes we spent last week on introducing stream ciphers can essentially be reduced to this drawing here. Okay, that's where we ended up with. That's where we kind of stopped, and now the challenge is what's in here. That's really what a stream cipher is about, and you can also more formally you could call that the key stream generator, because this is here the key stream bits. What we also talked about last week is one way of doing that really super secure, namely if you use the original key here at this point. So if you don't have this box here, but you directly add the key bits to the plain text, and that's called the one-time pad, and that has is provable secure, so it's really beautiful. But it's really ugly because the key is as long as the message, so it's highly impractical. What we want to do now is step towards real-world stream ciphers. Look how they are constructed in the real world. And of course, we could spend a whole lecture, so we could spend the next, 10 weeks or so on dealing with stream ciphers. But I just want to, what we want to do now is to give you one, like a basic building block, an LFSR with which you can build stream ciphers. And then we also, it's one of the few times in this whole lecture series where we show you an actual attack. So we show you a way of building a stream cipher, show you that it's weak, and then you might wonder, why are we doing that? Why are we here today? And it's because if you use combinations of these building blocks, you can build something very secure. So we show you like the basic building blocks for building stream ciphers. So program today, the chapters, if you wish, of the lecture are introduction to LFSRs, whatever that is, linear feedback shift registers. We're going to talk about that today. Secondly, want to talk about general LFSR. So how do we, beyond the introduction, and talk a little bit about properties. And then probably the coolest aspect of today, we're going to talk about attacks. Let's start with the introduction to linear feedback shift registers. Okay. Or LFSRs. Okay. So what is that? I'm not quite telling you what that is, but what we use it for. Kind of the motivation I want to give you first is goal stream cipher and again we talk about stream cipher, we talk about these boxes here with the question marks in it. Okay, so we want to have a construction for this. Can we tone down? Can we tone down? Thank you. So building something, that goes in here instead of the question mark, a stream cipher, that is small. And when we talk about small, what we really mean, or historically what people mainly meant when they said we want to have a small cipher, is low power. In hardware. We torture you also with introduction to electrical engineering, right? Most of you notice that, right? It's not only crypto that you're learning here. And if you're wondering, well, why do we need that? Today is the time, okay? So today I really show you some electrical engineering kind of thing where you have a direct interaction with cryptography. To motivate that a little bit more, You see this here. Showed you that. This is in my cell phone, okay? It's the A5 cipher, okay? I asked that before, right? Everybody has a cell phone. Anybody without a cell phone? No, nobody. So everybody who has a cell phone, probably at this moment you have in your backpack or in your pocket, you have this baby there, okay? That's the stream cipher, okay? And you're going to understand that much, much better in 80 minutes from now, okay? Because you will get a pretty good idea how that basically works. What you see in particular, I think now it should become even clearer. I'll switch. It's gone again. Oh, I can't believe it. The picture is gone. That's going to come up hopefully in a minute again, that picture. However, so you saw a weird drawing, right? And I'm going to explain that weird drawing, right? Example. What you saw before is the A51 cipher in GSM, okay? And this cipher consists of 3 LFSRs, okay? So the question, what is an LFSR? And that's pretty much what this lecture is about, okay? What is an LFSR? How can we use it? And then also we show you how to attack that. And this is always if you use a single LFSR. And as you saw before, A5 uses 3 LFSRs. So you have to use them in combination. And if you're clever, you might end up getting something secure. Okay. Here, okay. So the smallest element what a shift register consists of, a shift register is a concatenation, Verkettung, atomic element of simply a flip-flop. You want to know what a flip-flop is in electrical engineering, computer engineering? Any ideas? What is a flip-flop? What does it do? Yeah, it stores something, right? What it does is stores a single bit, okay? Stores 1 bit. The symbol is something like that. You have an input, 1 bit input, 1 bit output, here, input, output. And then you have a clock input, okay? And the clock input kind of determines when a bit is to be stored or not. Okay, now we're getting a little bit more EE-ish, electrical engineer-ish. Okay, let's say we have a, if this is our input, and let's say the input generates this signal, 0, 1 sequence, okay? This is time here, okay? This is a timeline. Here. That means the input always goes up and down, right? This is a 0 bit, a 1 bit, 0 bit, 1 bit, okay? It's happening. So, and now we look what's happening on the output, and as long as the clock is low, nothing happens. That means the output also stays low, okay? But if at this moment, if you generate a clock pulse, what this clock, this rising edge of the clock tells this flip-flop is, please store the input, okay? So the flip-flop looks at the input here, and what does it see? It sees a logical 1 here. Okay, so that means at this point the output goes to 1. And the interesting thing is, it's a storage element. That means even if the input goes down, the output stays 1, okay? And then if there's another clock pulse, let's say at this moment in time, again, the clock pulse tells the flip-flop, store the input value. And again, we look what's the input value. Input value is 0. Therefore, at this point in time, the contents of the flip-flop becomes 0. Okay. That's it. Not very complicated, okay? If you have a laptop with a Pentium chip, there are a few tens of millions of flip-flop inside, or equivalences of flip-flops. Let's put it this way, okay? A few tens of million transistors and probably a few 10,000 or so of flip-flops itself. There are a few million gates inside. Okay, so what we now want to do is, if you look back at this picture up there, we want to generate a pseudo-random number generator hopefully with cryptographic properties. Okay, let's maybe write that down. Let's try to build a PRNG. Okay, so we want to generate random bits using a flip-flop. Probably not one flip-flop, but several flip-flops. Okay, and now comes a very important drawing for the rest of the lecture, and you need about half a page. Okay, so who's ever taking notes and you come towards the end of your page, turn the page. We're not taking one flip-flop, we go really wild, we take 3 flip-flops, okay? Very complicated. Three flip-flops. I need the space here underneath for my drawings here, okay? So, and then we connect them. That becomes a shift register later. And this becomes our output signal here, okay? And now you're always, with the shift register and actually all systems, you need some kind of initial state. You have to start it with something. You have to load the flip-flops. You have to assign some initial value. And the value that we assign is 1, 0, 0. You can pick any other value. It's just any other value except the all 0 vector. But any other 3-bit value that has at least 1 1 in it, okay? So what we do now, so this is the contents of the flip-flop. So this flip-flop has a 0 stored. That means the output here have a 0, here you have a 0, you have a 1, okay? So what we do now is, so what is and this is the actual output. This is our SI here, okay? What comes out here. So what do we see at this moment in time? We see this 0 at the output line, okay? And now we have to do something, otherwise it stays 0 and it's not very exciting. So we start clocking that. Means we generate the first clock pulse, okay? How does this work now? If there's a clock pulse, as we've seen here, if there's a clock pulse giving to a flip-flop, the flip-flop stores the input value. Means if we go here, we generate a clock pulse here, something like this here, again. This flip-flop looks what's at my input? Well, its input is 1. That means the output value becomes the 1. So this one is shifted in there, right? The 1 is shifted from the leftmost flip-flop to the central middle flip-flop. Same here. We also have clock pulse here. What's happening here? Again, this flip-flop looks, what's my input value? Well, the input value is 0. So, and again, it stores this 0, moves here, and it means if this is S, what did I call that? S0, this becomes S1 with the value 0. Okay? Everybody with me? This is how a shift register works on a very basic, very slow level. So let's clock it again. So the next clock pulse comes. Let's look at this flip-flop here. Clock pulse comes, it looks what's the input value. Well, the input value here, because we have a 1 at the output, this input is 1, you get a 1 here at this point, okay? So this 1 is shifted to here, okay? So the third bit we see is a 1, and unfortunately, oh yeah, maybe. So what's happening to this flip-flop? We don't know, because this is empty, right? You get that? So that would be a really stupid random number generator, because we could only clock out these 3 bits, right? 0, 0, 1. We clock that 3 times, we get the 3 output bits, that's it. Okay, game is over. We don't want that. We want to have something smarter. We want to have a long output sequence. Okay, so now the basic idea is, so this is a shift register. So that would be, in terms of letters, LFSR, we only have the S and the R, shift register. You with me? Shift register, okay? So now we want to have a feedback. The basic idea is that we generate fresh input for this last bit here in every clock cycle. So, and what do? We compute, in quotation marks, we compute a fresh input bit for this leftmost flip-flop from the other ones. And how do we do that? One possibility of doing is saying you take this output, means the output of the first flip-flop, the output of the middle flip-flop, you take them, you XOR them together, and the result of this modulo 2 addition, or the result of the XOR, becomes the fresh input here. Okay? Very important principle. Try to get the beamer running again. Okay, now let's revisit our previous clock cycles here. So that was the initial state here, okay? And this 1, 0 was after the first clock, but we didn't really look into this here, which is really the interesting one. So remember what happened. Which value is clocked in here after the first clock cycle? Well, where's this input coming from? We have to go back here. And here you see that this is the XOR sum of this output, which has the value 0. And this was the value 0, 2. So what we have is a 0 here, 0 here. Everybody with me? It's kind of before the first clock cycle. That means you kind of pre-compute a 0 at this point here. Then you clock. And what's happening when the first clock pulse comes at this point here, we didn't even look at that before. This clock pulse assures that the contents becomes a 0 here. Okay? Let's erase it again. Okay. Now before the second clock cycle, what's happening is this flip-flop has a 1, so you get a 1 here. You get a 1 here. And this is a 0. Okay. So you have 1 and 0. What is 1 and 0 XOR? Does anyone know what the XOR is of this? 1, very good. So in preparation, before the second clock cycles, you have a 1 here. Now the clock pulse comes, you clock in a 0 and that 1, and this is a 0. Okay? So what you see here, this is always shift it over. Okay? And now I give you 2 minutes, and maybe they do the first 8 ones, you know, by yourself, okay, or with your neighbor, whatever, or watch YouTube, I don't know, okay? So I did 3 clock cycles here, right? Do the next 5. You have 2 minutes. Irmgard, könntest du den Damon mal bitten, ob er mal runter in die Vorlesung kommen kann, nach dem Beamer gucken? Okay, danke. Okay. Okay. Your time is up. You get the 111. 011. Did I skip one? Oh, I forgot one, right. 00, 1, 0. Danke. 1. 1. Okay, so these are the first 1, 2, 3, 4, 5, 6. Is this right? Yeah, I'll do one more. 1, 0, 1, 1, 1, 1, 0, 0, 1, 1. Okay, so I stop at this point here. So these are the first 7 clocks. 1, 2, 3, 4, 5, 6, 7. Okay, and now let's look at the output here. So what I actually see is always the state of this flip-flop. So this is 0, 1, 0, 0, 1, 0, 1, 1, 1. Okay, that's the output here I'm getting. If you look at these 3-bit, and now we look not that much as like a sequence of flip-flops, but as 3-bit words, which is another treatment. Can we calm down? Hello, this row. Yeah, don't talk. That's the deal here. don't talk when you're here. Okay. If you look at 3-bit sequences, you know, there are 8 different 3-bit values, right? 0, 0, 0, 0, 0, 1, and so forth. If you look at these patterns, you have all 3-bit patterns that they are. Which one is missing here? You know, this is 1, 2, 3, 4, the 7 different ones. Which 3-bit pattern is missing? Yeah, exactly. All, so we're complete except all 0, 1. Okay. Now let's clock that baby again. What's happening here? We have a 1, which is transferred to the left-hand input. So the next clock cycle would be this value. Okay. What is special about this value here? What's different about the one before here? Yeah, it's the same as the first one. Okay. So this 1, 0, 0 is the one here. Okay. Does anyone know what is the next one? We don't even have to look at the flip-flops anymore. What will be the next 3-bit value here? What can I write down? 0, 1, 0. Why is that? Well, we saw before, if the contents is 1, 0, 0, and you clock it, you become 0, 1, 0, which is actually what's happening here. So what we do is we run into a cycle, Kreis, Zyklus, okay? So after the 7th clock cycle, 1, 2, 3, 4, 5, 6, 7, it goes in here. You know, then you run down here, then here. Okay. That means at the output, it will always be this bit pattern 0, 0, 1, 0, 1, 1, 1, and then again 0, 0, 1, 0, 1, 1, 1. So this was S6, you know. And then you have bit number S7 up to S13. S14 will again be 0 and so forth. Vielleicht musst du einmal ein- und ausschalten, das hat eben Christopher gemacht. Hast du schon? Control. Yeah. Okay. So that means this is a periodic one. All these deterministic ones are periodic. I mean, it's periodic. So, and what is the period? Well, the period is exactly this here. Okay, this is period of length 7. Okay, you have a length 7 period here. Okay, so all of this seems pretty electrical engineering kind of thing, right? You know, we have flip-flops and signals and, you know, timelines and pulses going up. But it turns out there's also very powerful mathematical descriptions behind these shift LFSRs, these shift registers, okay? And now we want to develop kind of the mathematics behind that, okay? Let's look at this very LFSR with 3 flip-flops, and let's see what we can do if you want to describe them in equations. Mathematical description. We're getting there. Okay. So let's go back here and let's look at the output. Now what we want to develop is here, the movie is here, movie is here. Okay, this is just PowerPoint. We want to develop some kind of description of the output bits. So this was the output bit as 0, and now I need color. This is as 0, which is really boring because that was the initial value, and maybe I should put these 3 bits, they're very, very special because they're very specially dull. Okay, they're really boring, they're langweilig. Okay, so they were initially loaded into this thing, so I just gave them to you. Okay, there's no math behind that. So this was the first boring bit showing up at the output. This bit was coming from here, that was also initial value as 1. And this is the third value, okay, which was the initial value shifted through. So it becomes really interesting with this bit S3, right? So the third or fourth output, depending how you count. Where was this coming from? Well, this was coming from here. This is great. Oder in die Mitte wäre am besten. Okay. Ach so, dann lass rechts, ist okay. Danke. Okay. This bit was coming from here, and now we have to switch on our brain for a moment. Where was this bit coming from? This 0 was the initial input here, which was computed as the XOR sum from here and here. Do you recall that? Where we got this 0 from? We have to look at this input, and this input, this is S3. It's initially that is S3, and where's S3 coming from? Well, S3 was the XOR sum of this here, which is S1. So this is S1 plus S0. Okay, so S3 is S1 plus S2 modulo 2. S1 plus S0, I'm sorry. S1 plus S0. It's okay, just leave it. You can do the same trick with S4. If you go back and look, where is S4 coming from? Well, this bit S4 was coming from here, And again, if you look at your diagram, you'll see that S4 was the sum of this bit and this bit, which is S2 plus S3. Modulo 2. No, S2 and S1, right? I'm sorry. Okay. So. Do you see a pattern if you look at this equation? If you look at the indices? 3, 4, 1, 2, 0, 1. We get the idea, right? So in general, if you look at bit S sub I plus 3, plus 3 is easier, so to write down. You can do anything here. It's just it's easier to do it a little bit easier to do it this way, because here you can add up Si and Si plus 1 modulo 2. So this is the equation that describes this shift register there. Okay. Si plus 3 is this here. Okay, that's it. Okay, so this is kind of nice. But it has the problem we don't want to use in our GSM phone, because you probably don't want to have an output that has a period of 7, right? Every 7 clock cycles you get the identical bits, right? This is not something very, very smart to do. What we probably want to have, what we would like to have, is a period of a few billion or something. Some really, really long number. We want to have a really long period, okay? Not just 7 bits and then it starts to repeat, but a few billion, trillion bits and then it starts to repeat, okay? And it turns out it's really easy to make the same thing much, 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 much longer, okay? And that's the next chapter of today. So we're done with the introduction. And now we want to, what we really did is we looked at a very specific, extremely short LFSR. And now we want to do something more exciting. We want to look, this is the second chapter for today, we want to look at general LFSRs. So allgemeine linear rückgekoppelte Schieberegister in German. So you get a really long drawing now from me. So we want to have now not a shift register with 3 flip-flops, but with an arbitrary number of flip-flops, namely m. So we get now a kind of a complicated drawing. If you don't want to do that, it's in the lecture notes. It's in the book, which is on Blackboard. Okay. So what we say this becomes, you know, flip-flop FF M minus 1. In the drawing before, that would be flip-flop number 2, okay? But now we don't have 3 flip-flops, but we have M flip-flops. M is a variable. And at the end, and then we have dots here, and at the end, the right-hand side of the shift register, this is flip-flop number 1, and the last one, the rightmost, is flip-flop index 0, flip-flop 0 here. This is the first thing that we do. So the first thing that we generalized is we jumped from 3 flip-flops to an arbitrary number of flip-flops. The first thing that we can manipulate. The other thing that we can manipulate, which is probably not, which is maybe clear to you, maybe not. The other thing that we can manipulate to have, like, to describe any LFSR is, what we did here is we took the output of this here, and the output of this XORed them and fed them back, okay? But we didn't take this here. We could have, right? We could have introduced another flip-flop here, and it just makes it with the best things. Don't copy that. It will confuse you at home, okay? I'm not doing it. So, but we could have done this here, right? But what we really could have done, there's three flip-flops and 3 outputs, you know? Output 1, output 2, output 3, and we can pick any of them, XOR them, and feed them back, okay? And what we did here, we took exactly 2, right? The first 2, but we could have all 3, or we could have picked this and this, or none of them, right? We could have done a lot. So now we describe that generally. That means each of these M flip-flops has a fair chance of being fed back, of being part of the feedback path, okay? And there's a kind of a weird notation to that. So what I really want to do is, first I'll show you what I would like to do is, which would be easier to understand, every flip-flops, and don't copy that. I'm going to erase that, ausradieren in a minute here. Every flip-flop becomes a switch, okay? And the switch is either open or closed, okay? But then with the switch, you don't get a very nice mathematical description. So what we do instead is, and don't kill me, we introduce a multiplier. It's really when we multiply with a variable, which is called P0, P1, P2, and so forth, okay? And I'll show you, I promise, in 2 minutes, I'll show you why it's a good idea to have a multiplier here. So the multiplier acts like a switch, okay? The multiplier stands for the switch, and again, in 2 minutes, you'll know what I'm talking about. Here you have a multiplier with the kind of the switch variable, P1, and you do that many, many times, and here you have a small multiplier of this here, okay? So what do we do now? We connect all the flip-flops together. Again, that's the shift register part of that. And then we construct the feedback network, which is always the same idea. You take the output of every single flip-flop, connect them to the multiplier, and then all the multiplier outputs are XORed together. It becomes one big XOR sum here. Okay. So the question might be here, what is the thing with the multiplier about? Why do we draw a multiplier? And it's pretty easy, okay? So we look now at, you know, one of these multipliers. Why do we introduce a multiplier here? It turns out, if you look at this here, if you call this, say, A and B are input and output, right? And we have this one of these variables pi here, okay? So this behaves as follows. This behaves like a closed switch, geschlossener Schalter, okay? If pi, if this p value, this p variable has a value 1. And why is that? Actually, it kind of makes sense because then you can write b, the output, is pi times a, but pi is 1, so this is equal to a, right? Because this 1 times a is 1, right? So in the other case, if the switch variable is 0, this is an open switch. So if this is 0, why is that? Because now b is 0 times b, which is 0, okay? It means this value is always 0 here, okay? That's how it works. Okay. Good. So what we're doing now is, can people roughly follow? Oh, and maybe that's important here. Pi are binary values, okay? All these, we call them some switch variables, Schaltvariablen, because they tell us whether the switch is open or closed. It's conceptually very, very simple. So what we're doing now is we want to stop doing the stupid drawings, right? It takes a lot of time, very engineering-ish. We want to introduce again a mathematical description for that baby here. We want to deal with them mathematically. In particular, when we start talking about attacks. You know, mathematics will be our friend when we start attacking these shift registers, okay? So let's look at the output bits that we generate, okay? Again, we need an initial value. That means there will be an initial setting which loads in S0 in here, S1 in here, S2, blah, 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 up to S index m-1, okay? So we cannot write down equations for S1, S2 up to Sm-1 because they are, you know, essentially God-given. You know, they're given in GSM, they are given by the protocol. Okay, so they come from somewhere. Now, it is interesting, how do we compute the first output after this here? The first non-trivial output is namely Sm, okay? And what we have to do now here, Sm is in this state, you know, if we loaded the initial values, Sm is being pre-computed here at this point. So we're interested, what is Sm is what here, right? This is what's being pre-computed here initially. Well, this is, we start maybe here. This is S0 times P0. Or I start from here, that's easier actually. This is Sm-1 times Pm-1, okay? This is which is this value, XORed Sm-2 Pm-2, which you don't see here, and so forth. And at the end, we have S1P1 plus S0P0, and again, everything is modulo 2. And that should be 3 bars here. Okay. So what you do here in every slice, ne, so eine Scheibe, you know, this is like a Scheibe here, a slice. You compute the flip-flop output, you multiply that with this variable p, and then you keep adding that up. Okay, you get this long sum here. This is Sm. What about the next bit, Sm plus 1? It's similar, except everything has been shifted. Okay. After what is the contents of this flip-flop? Was ist der Inhalt hier after one clock cycle? We don't have Sm in here, but we don't have Sm-1, but Sm is in here. So if you compute Sm plus 1 here at this point, well, you look, this contains an Sm, so this becomes Sm, but multiplied by the same p here, so the p stays the same. Plus S2P1 plus S1 P0 modulo 2. If you look at these two equations carefully, you get again, you see the pattern here. Here you increment m. What's happening with each of these products, Pm stays the same, and the S is always incremented, always increased by 1, right? You go from S1 to S2, S0 to S1, M-2 to M-1. So in general, this is a very powerful formula that you get now. In general, that means now you get a formula for any output bit. Any output bit as S sub M plus 1 is the summation symbol where you run from j equals 0 to m minus 1 Si plus j times pj mod 2 and I runs from 0, 1, 2, 3. And this is very important, so that should be a very, very big red box. Okay. So this equation, yeah. Very good question. Where is the PJ coming from? Where's the PJ coming from? So this you have to choose. Okay, this is the interesting part. Like in GSM, in your cell phone, this is festgelegt. Okay, this is fixed. And this is very good. This is essentially the big choice you can make as a designer. You can choose the PIs here, yeah, the PJs. And this is an excellent question, and it's not abgesprochen, right? He didn't ask him. I don't pay him, but it's a perfect question at this point. So really, what LFSRs are about now. Choosing those p-values, right? You can each p-value can be 0 or 1, and depending how you choose them, you get very, very different properties, very different Eigenschaften. Okay, so. Oh, yeah. Yeah. Thank you. This is 0 times a, right? So this would be PE mal A is equal to 0, right? And PI is 0. He could have left the 0 here. This is PI. Okay. Vielen Dank. Any more questions? Any more mistakes I made so far? No? Okay. Speak up. Okay. So, and again, it was an excellent question. What's the deal with this thing here? So this is kind of a pretty big description we have, and now we have shift registers. And now the interesting thing is what can we do with shift registers? And there are a lot of very, very interesting aspects. Okay, maybe the most important one is the following. Theory. Again, what we get out here is this SI sequence, so that means this runs from S0 up to something, and there will be, at some point, there will be a period, and then it starts repeating. And before we saw with 3 LFSRs, you got a period of 7. Maybe I should ask that. So here is period. This m, which is called the degree, it's the number of flip-flops is the degree, right? Does anyone see how they're related? Any mathematical formula where you get the relationship? Yeah. Exactly. This is 2 to the third, 2 hoch 3, 2 to the third. That's the English term for that. Minus 1, right? Where's the 2 to the 3 coming from? Yeah, exactly. And how is that related to this stuff here? Yeah. 2 to the m or 2 to the 3 is all the bit values we can generate here. Right? The 3 bit patterns we talked about, right? There's 7. There are 8 altogether. 2 to the 3 is 8 different ones. And I asked you before which one is missing. The all 0 one, which is this one here, right? And so it turns out in general, theorem, the maximum period, and in parentheses, in Klammern, or sequence length, length generated by an LFSR is of degree m, if you want to be exact, of degree is 2 to the m minus 1. There's a proof in the book, and it's actually maybe I just motivate the proof a little bit. So what's happening here is that as soon as you have one state, the state is the Zustand is simply the bit pattern stored in the flip-flops, right? If you have a given state, that means if you have a certain bit value, for instance, in the beginning you have this bit vector S0, S1 up to Sm minus 1. If this is given, it's completely clear what the next state is because you do this thing with the shifting and the XOR sum, right? So that means it's deterministic. So once I give you these m bits here, you can exactly tell me what the next state will be, right? The next Zustand. And now how many different states are there? Well, there are only 2 to the m possible ones, right? If you have m bits here, you cannot have 2 to the m plus 18 or something, right? Same here. There are only 8 different bit patterns with 3 bits, right? They're not 9. There's no 9th bit pattern. There are only 8 different bit patterns. And now it turns out, as soon as you hit one bit pattern for the second time, you end up in a cycle, right? So as soon as you have if you've reached one bit pattern, you exactly know what the next bit pattern is going to be, okay? So that means what the maximum thing that can happen here at this point is you get you're actually lucky, you're very lucky at this point here, right? Because we actually generate all different bit patterns. We had 0, 0, 1 here, we had 0, 1, 1 here, 1, 0, 0. There was no repeat. Let's say just a Gedankenexperiment, right? Thought experiment. If at this point, let's say the next state would have been 1, 0, 0, let's say it's this line, we would have cycled around here at this point. Do you know what I'm saying? As soon as you hit a previous bit pattern, you're stuck in a cycle. And so the longest thing that can happen is exactly this extreme case. You actually generate all different, in this case, 3 bit values, okay? With 3 flip-flops, you cannot generate more than 7 different states. If you have an 8th state, you must have one repeat. If you have a repeat, you have a shorter cycle. Okay, this is very hand-wavy, unexact, but it's more exactly in our lecture notes. Okay, so the very important statement comes now next, namely I'll do that as a theorem too. Theorem only certain feedback configurations What do I mean by feedback configurations? I mean, the feedback is everything that's here in the upper part of the drawing. So only certain set of PIs, depending how the PIs are chosen, only certain feedback configurations and the feedback configuration is the set of p-values, right? P0, P1, so this is a bit vector, right? Remember, this is a bit vector. So only certain configurations geben uns maximum maximum length sequences. Punkt. Okay. You probably have no idea what I'm talking about, but I'm going to give you an example now. First example. So we look at LFSRs of degree 4. And first I give you this here. P3 is equal to P2, is equal to P1, is equal to 0. And P0 itself is 1. Okay? That means I do a very quick and dirty drawing here, not as elaborate. So if M equals to 4 flip-flops, what about this switch here? Is it open or closed? Any ideas? Closed. Why closed? Well, this is P0. Is at this point here, right? It's the rightmost. Ganz rechts, right? And if it's equal to 1, it's a closed switch. So this one gets a closed switch here. Okay. What about the next one? Is it open or closed? This is P1. It's open, right? So, and I don't even have to draw it here, right? I don't have to draw an open switch. What about P2? Open or closed? Open. P3? Open. Okay. Oh, I'm sorry, right? I was off here. P0. I'm sorry. This is equal to 1. And the first one needs to be closed, I'm sorry. So the first two are closed, the next two are open. Okay, so we have this here. Okay, so here is the this, if you do the same thing again we did here, you get a sequence length of 15, okay, the maximum one, okay? This is example number 1. Now let's look at another LFSR. Again, degree 4, so 4 flip-flops. But this time, we close all the switches. We make it really complicated, right? Here we only close 2 switches, 2 were left open, now we close all ones. So that means P3 is equal to P1, P2 is equal to P1 is equal to P0, and they're all 1, okay? And now if you close them, of course, you get this drawing here. You get this here, okay? And by intuition, our Gefühl, at least for me, it always tells me that looks more complicated, right? There's a better scrambling, bessere Durchmischung, but it's not. This is actually cryptographically or statistically, that's not as nice, because here you get a period of 5, okay? That means whatever you put in here as starting values, it always cycles around after 5 clock cycles. So the period here is 5. If you don't believe me, wait for the homework assignments, okay? There will be many of these very super interesting. Okay. So now comes a kind of a weird thing, namely a notation. LFSRs are often specified by what? So what do I mean by specified? I don't know whether that's clear to you, but what I've showed you here in order to know what an LFSR is in great detail, there's only 2 things I have to give you. I have to give you the degree, you know how many flip-flops there are, and I have to give you this vector with P, right? With these P's, right? So this would be, you know, 1, 1, 1, and 1 in this case, right? If I give you the vector of, if I tell you there are whatever 4 flip-flops and the switches are closed, 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 everybody can do this drawing, right? You can also do that for larger one. You saw before in our cell phone, the LFSR are somewhat bigger, so they have a length of between, I think, 19 and 23 or something. You know, so there may be LFSRs of degree 20, of length 20. The only thing I have to give you, I have to tell you, well, it's 20, and I have to give you this 20 bits for each of the switches here, right? And then you can sit down and draw this here, right? For weird reasons, mathematical reasons, this is not what people do. What people do is they write them down as polynomials, and it's kind of a very different meaning of polynomial relatively to what you used from Gymnasium. Namely, rather than giving you like a drawing or this vector with the PIs, you get a polynomial, but it's a very easy thing. You always, degree m LFSR always starts with x to the mth, and then the coefficient of xm minus 1 of the next power here is this p here, which is exactly this switch variable we had before, plus p1x plus p0, okay? you look at an example, I go back here to the drawing we had before. So what would be the polynomial here at this point here? For this, LFSR would have the polynomial P of x is equal to, well, you have x to the 4. You know, this is what I just told you. Then we have to look what is Pm minus 1, what is P3 is 0, P2 is 0. So the next one you have is 1 times x plus 1. Okay? The polynomial for this baby here is p to the x plus 1 times x cubed plus 1 times x squared plus 1 times x plus 1. And of course, you can drop most of the ones here. So this is okay. So your life changes from now on, okay? So if somebody gives you this polynomial and tells you, we're talking about stream ciphers and LFSRs, what's happening in your brain from now on, you see this circuit diagram, okay? So this circuit diagram is the same as this polynomial when we talk about LFSRs and stream ciphers and crypto, okay? It's just the same thing. And why is that? Because if you deal with them as polynomials, you can look at polynomial properties and you get very nice results. For instance, by looking at polynomials, you can determine when an LFSR has maximum length, okay? Maybe I'll write this down, one last theorem. Okay. Okay, so what you see here, for instance, these are primitive polynomials, what we call primitive polynomials. And can I do that here? For instance, do you see this here, 0, 1, 4 here? Can you see that? Can I highlight that? Oh yeah, this is cool. Do you see this one? Does this sound familiar? This is this polynomial here, right? X to the 4 is there, the 1 coefficient is there, and the 0 coefficient is there, okay? And this table, which is in your lecture notes, which is in our textbook, has a table of all what's called a primitive polynomial. You see the headline, primitive polynomials for maximum length LFSRs. So in practice, you get them out of tables. You can also compute them. Roberto Avanzi from the math department, when I wrote the book, I told him, give me the first, 128 primitive polynomials, and he computed this list for me, okay? But let's maybe write that down as one more statement. Only LFSRs with primitive, and that should be in quotation mark in Gänsefüßchen, with primitive polynomials yield maximum length sequences. And now the question is that you should ask what in the world is a primitive polynomial, and we're not really doing that here. It's too early in the first semester. It's roughly speaking somewhat related to prime numbers. You know, these are polynomials that don't factor. So you cannot break them down in smaller factors plus one additional property. And again, primitive polynomials, see textbook. Okay, there's a list. And if you Google that, if you look at Wikipedia and stuff, you find many, many tables with primitive polynomials. So, which brings us to the last part of the lecture. Oh yeah, one important thing here is this is a very powerful statement. So the length you can generate is 2 to the m. And if m is 3, you get something, you get the sequence length of 7, which is a joke, right? Which is far too short. But if you choose here, let's say m equals to 100, you get a sequence length of 2 to the 100, which is huge, which you will never finish. You will never cycle through the sequence. 2 to the 100 is a far too big number, okay? We can do with, a lot of all computers on planet Earth, you get maybe 2 to the 70, 2 to the 80, if they run for 10,000 years or something. You will never be able to, get into this cycle here, okay? But then using 100 flip-flops in a row is pretty short, right? We don't need a computer the size of this room to build 100 flip-flop with a shift register with 100 flip-flops. It's very, very short, okay? That means with shift registers, we have a very powerful way, a very good tool of building extremely long sequences with very little hardware resources, okay? So from now, it looks really good. What's also good, what you don't know, if you look at this output, and again, not length 7, but let's say length 20, okay? If you look at the output you get here, you have very good random statistic properties. So the randomness properties, the statistical properties are very good. That means the sequence you get out here, even for moderately long one, length 20, that is a pretty good approximation for a sequence, a Null-1-Folge, you would get from coin tossing. Okay? So statistically, they're very beautiful, right? They're very easy to build, very nice statistical properties. So by now, we are tempted, wir sind versucht, let's use them directly in a cell phone or for email encryption, right? And what we're going to show you now, and it only takes us 10 minutes or so, I'll show you that they're very, very easy to break. So here we have something which is very small, very good statistical properties, very good randomness, in quotation marks, but you don't have this unpredictability. Remember last time we talked about PRNGs, pseudo-random number generator, in cryptographically secure ones. And this is one which is a really good pseudo-random number generator, but very bad cryptographically. And this, why is that cryptographically bad? I'm going to show you. I think it's maybe the most exciting part of the lecture. And whoever is sleeping now, wake up, okay? So this is really, in mathematical terms, this is the most interesting, challenging part of the lecture. Attacks against single LFSRs. So the attacker is usually we refer to as Oscar. So Oscar's goal is the following. Oscar knows we're using a stream cipher. He knows we have this situation here. And what he would like to have, he would like to compute all the SIs here, okay? What we now assume is, what's given for, given means given for Oscar, all YIs. That means he has all ciphertext, obviously, right? I mean, if he doesn't have the ciphertext, forget it, right? This is mind reading, Gedankenlesen. So he must know the ciphertext. Secondly, he knows the degree m of the LFSR. If he doesn't know, he can guess. He will see it's a very fast attack. If you don't know that, you just guess it, and you try all different m values. And then thirdly, which is probably the strongest assumption here, this is he knows x0 up to x to the -1. So he knows the first few plaintext bits. He knows x1, x2 up to x index 2 to the m-1. Okay? The first 2 m bits he knows. Okay? If you're wondering what is that, and I think we talked about it last week or the week before, what kind of information could that be? Why would he know that here? Does anyone know which situation? Why would he know the first few bits but not the next few bits? What is, yeah? Header information. You know, totally. If you open a Microsoft file, Microsoft Word or whatever, with an ASCII editor, you see this really long header information, which is always the same. So this is a quite realistic assumption, I'd say, in many scenarios. Okay. So the first thing that he can do is, since he knows that yi is computed as xi plus si mod 2, he can compute just by bringing solving the equation for si, he can recover si, the first si is here. So he can do that for, very importantly, for I running from 0, 1 up to 2 to the m-1. Okay. This is, if you want to be more systematically, maybe that's not. This is the first step of the attack. Is Oscar computes the first. We're here. Oscar computes the first 2 m output bits of this here, right? He knows there's an LFSR in here, right? Right, and he doesn't know how the LFSR look. Maybe I should have said that earlier. So he wants to recover this LFSR. Okay. Second step is now this goal. Recover S2 to the m, S2 to the m plus 1, and so forth. You would like to know all subsequent bits here that come out of your stream cipher generator. Okay. So the question here is, if he has a degree m, what is the only thing that is missing? Which part of the what's it? Exactly, the PIs are missing. The switches. He knows the m p values, so the m switch variables. He doesn't know what they are. And now I show you a very great, cool trick how to compute the PIs. Okay. So P0 is what, P1 is what, and so forth up to Pm-1. He doesn't know what that is. Okay. So what we can do is we go back. Essentially, the only thing we have to do now, we have to use this equation. That's probably the most important equation of the day, okay, of these 90 minutes. So, because we write down an equation for now what we want to have equations that involve the PIs. These are unknowns, right? We want to end up with some kind of formula or an algorithm for solving that. So what we do is, first we write down an equation for Sm. How was Sm computed? And we do exactly what we did here, right? We take exactly the same equation here. This was Sm times, no, Sm minus 1, sorry, times P, M minus 1 plus blah, 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 plus P0, S0, mod 2. Okay, so now we have one equation, and the good thing about it, what are the unknowns here? Unbekannten. I should switch that here. What are the unknowns here? Well, Pm minus 1 is known, unknown, blah, 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 up to P0. They're all unknowns. We don't know what the values are, okay? So the good thing is we have an equation that involves all the unknowns. The bad thing is we have one equation, one linear equation with m unknowns. This is not enough, right? You know this from whatever, Mittelstufe, right? Linear equations. We have m unknowns. How many equations do we need? M, right? We have one. Okay, so the question, where do we get the next equation? Yeah. Exactly. Yeah. Exactly. We take all these equations that we can get out of this formula here, right? You know, this was the first equation, second equation, third equation. So we let I run here at this point, okay? So the next equation we get here would be the equation for Sm plus 1. The Sm changes, but just what your colleague just said, the unknowns, they stay the same. This is nice. Right? Die Unbekannten, they don't change. They stay in the equation. Mod 2. Okay, now we have two equations, two unknowns. It's not enough, but we can do the same trick over and over again, and we do that exactly as the student said. We do that m times. That means here we generate m equations. So this runs up to 2 to the m minus 1. Okay, so this is now our system of m linear equations with m unknowns, Unbekannten. And now, and you probably had it just in Mathe 1, right, first semester, well, how do we solve that? What kind of algorithms do we use at this point here? What is one Stichwort, one keyword? Yeah. Gaussian elimination. Yeah. Okay. Can easily be solved with Gaussian elimination or matrix inversion. There are all kind of tricks, matrix. So lesson learned, this is a very, very, very important consequence, okay? If an attacker knows, and in Klammern, in parentheses, at least 2 to the m output values of an LFSR, comma, he can recover the entire LFSR configuration Oh yeah, we're not quite done. What does he do with the PIs now? You feed that into your Gaussian elimination. You can sort of on the internet. There are probably all kind of implementations that do that for you. What does he do if he gets the PIs here? What is the next steps then? He's not really interested in PI. He wants to know the plain text here. Yeah. Exactly. Now the PI completely specifies the LFSR. That means he can sit down, he can build the LFSR himself, right? He knows his PIs tells you switch closed, switch open. So he can build the LFSR. He has the initial value. So from now on, the third step here would be generate all SIs, right? He generates all SIs, and then he can XOR them with here and here 1. Okay. Maybe I should do that here. Third step, using PM-1 up to P0, build LFSR compute S0 as 2 to the m minus 1. And now it's interesting. He can now generate 2 to the m as 2 to the m plus 1, and so forth. He can compute the entire output. Okay? And now decipher. What does he do? He can now compute xi is yi plus si mod 2 and the interesting things are the 3 dots here at this point, right? He can do that for all I values. He can recover the entire plain text now. Okay. And one word at the end, one last statement. So what we did the last 90 minutes, I showed you ways of building these funny things, with a really long sequence length, and I just told you that statistically they're very nice, but they're easy to build. They have some weird mathematical description. And then at the end I showed you, oh, by the way, they're completely unsecure, right? Don't use them, they're really stupid, right? So you could argue it's really dumb what we're doing here. But if you use them in a combination, and this is, again, what in everybody's cell phone, everybody here in the room has a cell phone, you told me last week, all the hands went up. If you use them, for instance, the way GSM does, and they use 3 different ones together, and they clock them irregularly, they become fairly hard to break. Okay, so if you use them as a building blocks, and if you use several of them together, you can build something very secure. That's it for today. Thank you very much.